So for 2.3, the only thing I want to show you is a tangent. So in 2.1, I drew in the video what a secant line was. What does a secant line calculate? Alex? The average rate of change. Okay, so the average rate of change is a secant line. Okay, so if I had a parabola or a exponential function, if I find the average rate of change from this point to this point, this is called the secant line. Okay, so this was a secant. It's what you do when you're calculating rate of change, average rate of change. You know, every time you do average rate of change, you're actually calculating the slope of a secant line. Okay, when we do instantaneous rate of change, we are finding the slope of the tangent line. So this is what a tangent line is. So I'll use the same example. So average, we're looking at multiple points. So it's at two values. Okay? Or instantaneous, we're looking at 1 point. So what a tangent line is this. If I could draw this. It's a line that touches the graph at only 1 point. So secant is multiple points, so 2 points, so it's an average. Tangent line only touches the graph at 1 point. And I'll explain why it says within a small interval. I'll give you guys a minute. I'll explain. Secant line is average, tangent is instantaneous. It touches the graph at 1 point only. You just have to be careful. Say you had a graph that looked like this, which we'll get into the next chapters. When you're drawing a tangent line, so say I was doing the instantaneous rate at this point, so my tangent line would go through here. Okay, so we're finding instantaneous rate at that point. Do not extend it, like it will hit here, but we're not worried about that. When we're doing instantaneous, we're just worried about just that point. So for here, here. Okay, yes?
Wait, wouldn't, I thought the line had to be like, so that it's like, say it was like that underneath, I thought the line had to like have equal spaces on each side. You know what I mean? Like if it was like a.
Well, this one will, if it was right at the top, it would actually be this way, the tangent.
Yeah, yeah, so it would be even on both sides.
But I should have just did this one, so it should be this way.
Oh, okay.
Sorry, that was a bad drawing. I was just trying to include the top part, which is actually 2.5. So if I was doing the tangent line from here, this is actually 0. But I'm just looking at this point. Don't continue the tangent to touch another point. We're not worried about that one. We're worried about at that point. Okay, whereas the average connects to different points, where tangent's just 1. Okay, so that's why it says within the small interval, because they don't want you to extend the interval. They want a small piece. Okay, so that's tangent and secant. That's the whole lesson for 2.3. Okay. in the past, I've given an example, did a little bit of homework, but we don't have to do any homework for 2.3. I just want you to know that that tangent line touches at the graph at one point. And no homework for 2.3. All right. I took my grade 9 lesson. I'm not lying. I took my grade 9 lesson and threw it up here. Distance time graphs. So in grade 9, you learn distance time graphs. It's actually in chapter 2 as well, grade 9, 2.6. We're supposed to expand into speed time graphs, but we're not going to touch on those. So this is kind of just a refresher about distance time graphs. Because distance and time is speed, so which is free to change. Okay, when I ask you to describe a graph, a distance time graph, we want to include two things, direction and speed. So you have to tell me something about the speed, and you have to tell me something about the direction. Okay? So direction is just going away or towards something. So I had a graph here. So time is always at the bottom. Time is always on the x-axis. Distance is on your y-axis. If the graph is going upwards towards the right, if this was a graph of someone moving, would they be moving towards an object or away from an object? Grace? Away. Okay? It's going away because your distance is increasing. Okay, your distance is getting further and further away. So this could just be you going away from your house. Okay, or moving away from the car, from the park or something, or leaving school. Okay, so we're moving away. We don't know what it's moving away from, so we don't have to say it. So we're just moving away. And now we have to mention something about speed. There's actually two things we're going to mention about speed. How fast we're going, and if the speed is changing. Okay? So what would you want to add to this, Sandra? So moving away at a constant rate. Good. So that's one part. So when I say constant rate, the speed is not changing, it's constant. And how do we know it's a constant rate? How do we know that from the graph, that it's a constant rate? Go ahead.
Because if it was accelerating or decelerating, it'd curve.
It'd be curved. So this one is a straight line. So anytime it's a straight line, it's automatically, it's a constant rate. Okay, so we're moving away. Okay, and then we want to talk about speed. Are we going fast? Are we going slow? Okay, how do we distinguish between going fast and slow on a graph? Haley?
The faster it's going, the steeper your line.
Good. So the faster you're going, the steeper the line is. Okay, so if we had a line that's like this would be considered slow. And if we had one that goes like this, that would be considered fast. Why? Because the distance here, so if this is 1 and this is 2 meters, it's taking you a long time to move 1 meter, long period of time. Whereas this, your distance is increasing rapidly over a shorter period of time. So this is fast, this would be slow. And if you're not moving, what's the line look like? If you're not moving? Straight. Straight, yes, they're all straight. Horizontal, good. So horizontal being you're not moving, right? So horizontal, there's no change in your distance as time continues. Okay, for this one, I would consider this, let's say slowly, moving away slowly at a constant rate. So moving away slowly at a constant rate. Okay, next one. What's my direction now? Towards or away? Moving towards, Catherine? Towards, okay, because it's going down, your distance is decreasing. So moving towards whatever it is. And what about my speed now? It's curved, so it's changing, so it's, okay, or decreasing. Yeah, decelerating, well, we'll just say decreasing speed. And how do we know it's decreasing? So we have to look at the steepness, right? So this, I always break it into three parts, these. So this is almost going straight down. So this would be fast. Okay, so this is moving fast. Okay, and then the slope changes here. So it's not going straight down anymore. It's kind of a medium speed. And then this is almost going flat. So we're coming towards a stop. Okay, so this would be slow. So if I'm going fast, medium, slow, I'm decreasing my speed. Okay, moving towards at a decreasing rate. You can say pace if you want, but it just say decreasing rate. Okay, here, moving away, going up towards the right, so moving away. Is my speed increasing, decreasing, or constant?
Increasing.
Brooke? Increasing, good. So we're going not very steep to almost very steep, so our speed is increasing. Moving away at a increasing. Okay, there's a couple in the homework to ask you to just describe it. If they gave you something, like if they said if this was your house is here at 0, 0, and you can say moving away from your house at a constant rate or at a decreasing rate. But for this, it didn't specify anything, so we just direction and speed. Good so far? Okay, just only one more example. So hang on here. 4 seconds, 9 seconds, 13 seconds, 15 seconds. I'm going to scale up to 15. And I want 40 meters. Distance. Time. a piece of graph paper, let me know. Have it here. Just let me know if you're gonna end up, I'll give you one. Just another minute. Okay, so Mike is 20 minutes from class. 20 meters from class. Okay? So what does that help us on their graph? That gives us our starting point. So our starting point is what? It is, let's go Grace. 0, 20. Okay, so our starting point is at 0 and 20. Good. He walks to his locker at a constant rate. What does the constant rate tell us? Linear, straight line, okay? Which is 40 meters from his class in 4 seconds. Where is my next point now going to be? Alexandra? 4 and 40. Okay, so 4 seconds later, he is at 40 meters. Okay, and now we're going to connect this. He then stays at his lockers for 5 seconds, then starts walking at a constant rate. So he's at his locker for 5 seconds. Okay, so what's the next part of the graph gonna look like? Sarah? Horizontal line to where? To 9. Okay, a lot of times I have students that will go to 5. Well, actually, that's more grade 9s. They'll go to 5, but it's 5 seconds later. So they'll go to, so we're going into 9. So 9 and 40. Okay, so for 5 seconds, or he is at his locker. I know the times don't really make sense because 5 seconds isn't very long. And then starts walking at a constant rate to class. Okay, so now we're going towards class. Okay, so we're going down. 4 seconds later and 30 meters from class, he realizes he is late, so he increases the speed the rest of the way. Okay, so first we have to have a straight line somewhere. So where's our straight line going to be? Because it says moving at a constant rate. How's that doing? 13:30. So 4 seconds later, we'll be at 13 and 30 meters from class. Ooh, I think somewhere here. Let's see. So at this point, he then increases his speed to class. Okay, it doesn't say how long, so we could either go to 14 or 15. We can't go straight down. Okay, you can't be in this 2 different spots at the same time. Okay, I get this. I don't get them in grade 12s, but I used to get this. They go, oh, he's back to class, and they draw this way, and then put a point here. Huh?
Grade 12?
No, not grade 12, grade 9s. I used to have that. Okay, and I would say, I said, they're like, oh, he's going back to class. And I said, well, you can't do this. I said, why? Why can't you do that? Looks good.
Are you asking us?
Yeah, I'm asking you guys. You can't go back in time, right? Time keeps going. Your distance go back to 0. You can't go backwards in time. Okay?
So, sir,
Yes.
because he doesn't like reach class near the set speed, can we make him speed up in half a second to reach class?
In half a second?
Can we do that?
Sure. As long as it's not straight down. You can't
Very steep.
warp over here. You can't.
Alright.
What's it called? Scotty beat me up. We just go from here to here. No time happening. Even time passes there. Okay, so increasing speed. So is my graph going to go up like this, or is it going to look like this? Which one? Have it? Is it Kayla, right? Yeah. The second one, right? So increasing has to be this one. So because it's going slow, 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 and then fast. Okay, steeper. So I just went to 15. If you went to 14, 14 and a half, or whatever, that's fine. You'd probably curve it at that point and then go where you like to.
30 meters in like 30 meters in like a second.
30 meters in 2 seconds. Yes. Okay, 15 meters in a second.
You know that we don't run to class.
It's fast. All right, it's not. They're just picking up numbers, right? Okay. So let me explain this last part. The homework. So it's 1 to 4, 6A, 7, 8, 8, and 10. Just do distance time only. I think it asks you for a distance time graph and a speed time graph. Don't worry about speed time graph. So in your homework, when it just says do a distance time graph only. Okay, don't do a speed. Same with 4C. Draw a distance time graph for 4C. Okay. If you see anything with speed graphs, you're not doing it. Sorry. So 1 to 4, 6.